talking about chemistry. Okay. If you are an individual that's actually going to peruse your textbook, what I basically have done with this lecture and your next lecture is kind of split chapter 2 into 2 separate lectures. It's quite a bit of material, and it's also pretty complicated material. And I really have found, and this was my experience as a student, just talking about the fact that we're going to talk about chemistry. Sometimes I can see the deer in the headlights look from students, because chemistry, biochemistry stuff is complicated, and it's hard for students to wrap their minds around and understand what I'm talking about. So I've kind of split things apart, and I also go fairly slow through these 2 lectures just so that I don't lose anybody, because it definitely builds on itself as we go. Things can become more difficult. So if I need to slow down, or if you need me to reiterate something, explain something, don't hesitate to stop me. Okay. So with that said, here on our first slide, I got another cartoon, kind of to demonstrate a theme that will be presented in this lecture. Not a very funny cartoon, but we've got some little blobby dudes sitting in the classroom, not doing a very good job of paying attention to their instructor at the big front of the room, because they've got their eyes pointed outside, where you happen to see some blobby ladies. I guess that's the ladies because they got the lipstick. But anyway, the kind of most important thing is you'll notice all the fellas inside the room have the positive symbol associated with their blobby body, whereas the ladies outside have a negative symbol attached to their blobby body. And that demonstrates a theme that you might hear when people talk about their love life, and that is what? Opposites attract. Okay. So we'll kind of keep that thought of opposites attract in the back of our mind. We'll get to that here in a few slides. Not quite ready to talk about that. So just keep that in the back of your mind for a little bit. All right, since we're talking chemistry, I want to just go ahead and define that right off the bat here. It's the science of the structure and interactions of matter. So obviously, talking about matter, what's matter? Anything that has mass and occupies space. So it includes living and non-living things. I look around the room, I can see, the table, the chairs. Those are pretty obvious. I can also see you guys and myself when I look at my feet and my hands and that kind of stuff. Those are all examples of matter. Okay, I have a little bit left of my Dr. Pepper here. Inside of my bottle is that Dr. Pepper. Dr. Pepper is a liquid and it is a form of matter. And I've just described 2 of the 3 phases of matter: solids and liquids. What we really don't have the ability to see, but it is present around us in the air, is the 3rd phase, which is gas. Okay, on a day like today, probably more so this morning, go outside, you take a breath out, you can see that cloud of vapor hit the air. That's the local form of water turning into a gas as we exhale out. So water is, one of the cool things on planet Earth, found in all 3 phases. But other gases in the air include oxygen, obviously, that we have to breathe, and CO2 that we exhale. But more than that, we actually have a lot more nitrogen in the air that we breathe, and it's significantly more. So once again, matter is anything that has mass, occupies space. Now that word mass is the amount of matter in any object, so it's the amount of it. Okay, the term mass and the term weight kind of get used interchangeably by a lot of people that really shouldn't be doing this, or shouldn't be using them interchangeably. Weight is the force of gravity that acts on matter, and the key difference between the 2, mass will not change, whereas weight can change. Where if you use the example of thinking about like your body on planet Earth, versus your body on the moon, okay? The amount of us, how much of a body we have, shouldn't theoretically change here on Earth versus if we were up on the moon, right? Okay, but if you step on a scale here on planet Earth, and then you step on that same scale and you take it with you on the moon, that number's not going to be the same because weight is affected by gravity, and gravity is a much stronger force here on Earth than it is on the moon. Okay, and that's why when you see the videos of, you know, like Buzz Aldrin and Neil Armstrong walking on the moon, they're kind of bouncing. Okay, the gravity is not forcing them to the surface of the moon like it is here on Earth. So does that make sense? Okay. All forms of matter, which once again, matter can be both living and non-living, are made up of atoms. And we talked a little bit about atoms in our previous lecture when we first talked about the chemical level of organization. Atoms are the smallest stable units of matter. They are extremely small. This sentence is not accurate actually, but I haven't changed it on purpose, and I'll kind of explain why. But 200,000 of the largest atoms would fit on the period at the end of this sentence. So this period right here. Okay, and I say it's not accurate because I copy and pasted this directly from your textbook, where the font was a little bit smaller than what you see here. So it's, you know, still very significant, 200,000. This period will be bigger than what you find in your textbook, so that would be, there's way more than 200,000. But just tries to put the point home that atoms are extremely, extremely small. Okay. An element is a type of matter that cannot be broken down into two or more pure substances. It is matter composed of only one kind of atom, and we talked a little bit about examples of elements important to us: carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, chlorine, that kind of stuff. We'll talk more about those here in just a couple seconds. Okay. We organize all the different elements known to us here on Earth into that periodic table. Okay, I'm not going to, you know, talk about every single element in that periodic table because not every element is important to us as a, you know, living thing. Okay. Compounds are pure substances that contain more than one element. You know, we use the example on Tuesday of glucose and DNA. We also, you know, I mentioned water. Water is made up of two different elements. It's made up of hydrogen and it's made up of oxygen, and that's why it's H2O. Now, when I say H2O, that means it's got two atoms of the element hydrogen, one atom for oxygen. And water, along with any other compound, has a fixed composition. Anybody know what I mean when I say a fixed composition? Composition refers to what like its makeup is, and fixed means it doesn't change. So a fixed composition means for example, H2O, that's water. Okay, H2O2, H3O, H2O4, those aren't water. That's something else or something that doesn't exist. Okay, C6H12O6 is glucose. Okay, it's not C12H12O6. It's got to be that specific composition. Okay, let's continue talking more about elements and atoms. Topics that we're going to spend the majority of our day talking about. Okay, an element is simplest form of matter with unique chemical properties. Periodic table or periodic table of elements can be used to organize basic information about the elements of the universe. Pictured up here on the top left of our page happens to also be the top left corner of the periodic table. Now, the periodic table is loaded with many, many boxes. As you can see, we've only got 5 of them, and that's fine. I didn't want to include the whole thing because it's really not necessary. But included in each and every one of these boxes is a different element, okay? And each box represents what one atom of that element is structured like. There are 3 major components that you are going to find in each box, okay? At the center generally is where you'll find its chemical abbreviation, which is either going to be one capital letter or a capital letter followed by a lowercase letter, okay? Sometimes it's super easy, H for hydrogen, Li for lithium, Be for beryllium. Sometimes it's not so easy, like in the case of Na, that's the chemical abbreviation for sodium. Okay. Now, you're not going to have to learn them all. There will be some. Sodium will be one of those that you will just hear so much this semester that it will become common and you'll be able to remember it. Okay. So that is the letter or letters. Above the letter and below the letter are two different numbers. The top number is what we call the atomic number. And I don't say it here, so it might not be a bad idea to write that out or put it in parentheses somewhere. Atomic number is the top number. And that tells you how many protons are in the nucleus of one atom of that element. So in other words, if I were to ask you how many protons are in magnesium, you'd be able to tell me 12. And how many protons would be in lithium? 3. Okay, it's a nice easy round number. The bottom number, and it doesn't say this, so you might want to write this down, is the atomic mass. The atomic mass number is not going to be perfectly round, like 1, 3, 4, 11, 12 that you see there. But for example, beryllium, its number is what, 9.0122. It's pretty darn close to 9, right? Okay. Lithium 6.941. You're just going to round to the closest whole number. So basically, we could say beryllium's mass is 9. Lithium's mass is 7. Okay. And this gives you the number of protons plus the number of neutrons. So you already knew how many how many protons are in that atom. Now you know the protons plus neutrons. So if I asked you, you should be able to figure out how many neutrons there are. For example, lithium is going to have how many neutrons? You said 4, you said 6, it's 4. Okay. How'd you get that, Avery?
Well, the top number is number of protons.
Yes. So you take the bottom number, which is around 7, we'll round up to 7, minus 3, because 3 is protons, this is protons plus neutrons. So if you subtract 3 from 7, that gives you 4. So now you know that there are 4 neutrons, 3 protons. Okay. How many neutrons would be in hydrogen? 0. Okay. We just round it to 1. 1 minus 1 is 0. Okay. Does everybody see where that's coming from? Okay. Like I said, not every single element of the periodic table is really that important to us. 26 of them are normally present in one's body, but just 4 of those 26, we call these the majors, make up about 96% of us. And I told you guys this the other day, it's CHON. Okay. I've got it listed here, oxygen, carbon, hydrogen, nitrogen, and that's just because of the oxygen is the most prevalent. But CHON is how I guess if you want to remember it, I don't know, notch, maybe that works, whatever. CHON's how I remembered it. And those make up 96% of us. 8 others, what we call the lessers, make up another 3.8% of us. Includes calcium, phosphorus, those are important in our bones, potassium, sulfur, sodium, chlorine, magnesium, iron, all play a different role or roles. And then there are 14 trace elements. There's very, 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 very small amounts, make up only about 0.2% of our body mass. Okay. I'm not going to ask you to know this table or anything like that, but it does list the majors and the lessers, gives you specific percentages for each of them, and then what they do. Okay, there you can see the oxygen, carbon, hydrogen, nitrogen. Okay, 4 majors, and then the lessers. It does not list any of the trace ones, so it included it because it's in your textbook. It's not somebody ask you to memorize them. Okay, so that's atomic number and atomic mass. And I've mentioned these terms, protons and neutrons, but let's talk about what those things actually are now. Protons and neutrons are called subatomic particles. Okay, and every single atom is going to have these different subatomic particles that give each element its unique chemical properties. Okay, now protons and neutrons are 2 out of the 3 most important subatomic particles, the third of which is called electrons. Okay, protons and neutrons are found within the nucleus of an atom. Okay, this morning in anatomy we talked about cells and we talked about the nucleus of a cell. Next week we'll be talking about cells in this class and we'll talk about the nucleus. Okay, we said the nucleus is the control center of a cell. It's similar in that it's not the control center, but it's like the dense core of an atom. Okay, and surrounding the nucleus are these electron shells. You'll hear me call them rings or layers. It's places where you're gonna find the electrons, hence the name electron shells, electron layers, whatever. But they surround the inner nucleus. Okay. Now each of the 3 subatomic particles has a different charge. Okay. The protons have a positive charge. It's easy. P for positive, P for proton. Easy way to remember it. For every proton, they exhibit a +1 charge. Okay, so if you have 6 protons, you've got 6 positive charges. Okay, neutrons are uncharged, or if you want to use instead of that word uncharged, I tell students think of it neutral. Okay, it's not positive, it's not negative, it's neutral. Neutral neutrons, easy way to remember it. Okay. And then where those electrons are in the cloud or ring or the layer or the shells are the negatively charged electrons. Okay, so you got positive protons, neutral neutrons, negatively charged electrons. Okay, same thing as protons. For the number of electrons that you have, that's how many negative charges there are. So if there's 6 electrons, there's 6 negative charges. Okay. In a normal atom, the number of electrons equals the number of protons. So in other words, if I go back to our periodic table little segment here, not only does the atomic number tell you protons, but what's shown here is also telling you the number of electrons. Okay, so beryllium, for example, has 4 protons. It also has 4 electrons. So it's got 4 positive charges, 4 negative charges, which means its overall charge is 0. Okay, because +4 and -4 equal 0. We call that a neutral atom. Okay, so this means number of positively charged particles equals the number of negatively charged particles, creating an electrically neutral atom, as I just basically explained. Okay. Now, those electrons are found in clouds or levels or shells or rings, whatever you want to call them, and each of those rings can only hold a certain maximum number of electrons. Okay. The first ring can hold a maximum number of 2. Okay. The second ring can hold a max of 8. The third, 18. Bada, 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 bang. Keep going. You could add more. Okay. Now, that's not super important, okay, to talk about too in greater detail quite yet. Okay. But looking here at our 2 illustrations, this one's the one we kind of refer to the most, the show model. It's going to be easy to tell you how many electrons are in that atom. You can see each black dot represents an electron. Okay, 2 are able to go in the first, 4 more are able to go in the outer. Okay, so total number of 6. Okay, I can tell you right away, and it's because I know this, but this is an example of carbon. Carbon has atomic number of 6. Okay, atomic number once again tells you that there are 6 protons. You can't see all the 6 red dots. There's one hidden, but there should be 6 protons in there. which would equal the number of 6 electrons that are on the outside, okay? And then the little grayish, bluish dots that you see in the center, this is the nucleus, by the way, are the neutrons, which you can see have 0 or no charge, okay? Now, there are situations, not a ton of them, where you might find that there are different forms of the same element, like the 3 examples at the bottom, which are isotopes of hydrogen. In other words, they're just different forms of hydrogen, which the big difference is they differ in mass, okay? They don't have any change in the number of protons and electrons, but they do have a different number of neutrons, okay? They go by hydrogen, deuterium, tritium, or this is also going to go by protium. Hydrogen 1 has atomic number of 1 proton, 1 electron, and no neutrons, okay? Hydrogen 2 has 1 proton, 1 neutron, which is why we call it hydrogen 2. It's got an atomic mass of 2. Tritium has atomic mass of 3, 1, 2, and 3. Okay. What is in the periodic table is always the most commonly found form of that atom. So most of the element hydrogen that you're going to find is that first one, hydrogen 1. Okay. And it's by far and away the most common form of hydrogen. And most isotopes are stable, means that their nuclear structure doesn't change over time. But there are examples where isotopes are not so stable, and we call those radioisotopes. They're very unstable. And basically what happens is their nucleus kind of breaks down. We call this decay. And in doing so, lots and lots of radiation in the form of energy, or energy in the form of radiation, I should say, is given off, which can be very harmful to your health. Okay. You've probably heard of UV radiation. Where does that come from? Sun, okay? And if you are exposed to enough UV radiation, what can it cause? Skin cancer, okay? Radiation from nuclear power plants can be very dangerous and deadly. If you've ever heard of Chernobyl, you guys ever heard of Chernobyl before? Back in, I think it was the late 80s, I can't ever remember what year it was. There's a city in Ukraine that had a power plant, Chernobyl, that had an accident, and the power plant had meltdown, and a lot of people died during that meltdown right then and there. But the people of that city were exposed to lots and lots of radiation, and a lot of them for the next several years suffered from cancer and were going to die as a result. And at the time of the accident, they had everybody pack their stuff up within a couple of days and had them evacuate the city. And ever since then, nobody's really allowed in that city without government approval and without wearing a special hazmat suit, wearing a radiation monitors to make sure that their body is not picking up too much radiation. And that was 30, 40 years ago, long time ago. And it will still be cut off from civilization for quite a while, because it's going to take a long time for the amount of radiation to go down to a safe amount. Now, with that said, there is some good to radioisotopes. Okay, some of them can be used as tracers. They like highlight certain substances in the body and detect certain diseases in the body, like what you see there in the table with the different examples. Tactinium 99 used in imaging all the way down to thallium 201, helpful for diagnosing heart conditions. So it's kind of cool that, something that sounds so awful can be so great and useful. I kind of, talked about Chernobyl. That's a very extreme, drastic example, but one nonetheless. So, okay, so those are isotopes. Let's talk now about molecules and compounds, which is something we're going to do for the next several slides. I will be honest, I use these terms interchangeably when I really shouldn't, but I'm not a chemical engineer or a chemist or anything too in detail with chemistry, so I can get away with it. But if my buddy that teaches chemistry on campus caught me doing this, he'd probably yell at me. A molecule is where you have two or more atoms that are sharing electrons. Okay. And the molecular formula tells you and indicates the elements and the number of atoms of each element that make it up. For example, O2, what we commonly call what? What's O2? Oxygen. Oxygen gas specifically. That's the oxygen that we breathe that gives us life. Tells you that there is one element involved. That's the element oxygen. And then the little 2 there tells you how many atoms there are of that element. Okay. Now that's an example where it's only one type of element, but there can also be 2 different kinds of elements or 2 different kinds of atoms that may form a molecule. As we've talked about, H2O being water, C6H12O6, as I mentioned, is glucose. C6 tells us that there are 6 carbons, 12 for hydrogen atoms, 6 atoms of the element oxygen. Now, a compound is a substance that contains atom of 2 or more different elements. Okay, so in other words, O2 is made up of the same element. Okay, it's not a compound. H2O, C6H12, O6, glucose, water and glucose, 2 or more different elements. So these are compounds. This is not a compound. Does that make sense? So that's kind of why I use them interchangeably. I might say that compound of oxygen, truly it's not, but for this class, it's perfectly, fine. I just wanted to make sure I keep that, get that out there and let you know that most of our atoms in the body are going to be found in the form of compounds. Examples, as I already mentioned, is water. Another example, sodium chloride or NaCl. Anybody know what sodium chloride is most commonly called? Table salt. Okay, free radicals are an electrically charged atom or groups of atoms with an unpaired electron in its outermost shell. So you kind of just focus in on the outside, and you're going to find that there is going to be one extra electron, and having an unpaired electron makes them very unstable, highly reactive, and destructive to nearby molecules. Okay, think of them like a tornado, or if you grew up on cartoons like the Tasmanian Devil, okay, running around and bumping in and just being bad to other stuff, destructive. Okay, what they do is they try to become stable by either giving up that electron or by snagging an electron from somebody else, from another molecule, which can lead to breakup of body molecules. Okay, this morning when we talked about lysosomes, a type of organelle, I said that lysosomes help neutralize these guys. I also mentioned that free radicals are very commonly known for causing cancer, and that's obviously a bad situation. So superoxide free radical O2 is an example of a dangerous free radical. We commonly produce these, but we have hopefully methods, lysosomes and other organelles that can clean them up. Also, just eating fruits and vegetables is a great way to help prevent free radicals. You guys ever heard the term antioxidant or antioxidants before? Okay, antioxidants are great at neutralizing free radicals. Any fruit and vegetable probably going to have lots of antioxidants. A lot of times, if you like to drink green tea, you'll see on like the bottle of the green tea it says great source of antioxidants. And so, if you ever wonder what an antioxidant does, now you know. All right, time to talk about chemical bonding and chemical bonds. Chemical bonds are defined as the forces that hold together the atoms of a molecule or a compound. So going back, we just learned what a molecule and a compound is: an O2, H2O, C6H12O6 molecule. Okay, putting atoms together, okay, and making something bigger. That's what chemical bonding is. Okay. Now, it all is dependent upon something that we call the valence shell or layer. So let me read through. The likelihood that an atom will form a chemical bond with another atom depends on the number of electrons in its outermost shell, what we call its valence shell or valence layer. Okay. So going back to my picture of carbon, okay, I can look at this picture and tell you that carbon is not in a satisfied state, okay? And I can do so just by looking at its valence ring, valence shell, valence layer, whatever you want to call it, okay? And I'll explain why. An atom with a valence shell holding 8 electrons is said to be chemically stable, meaning it's unlikely to form chemical bonds with other atoms, okay? We always want to have 8 electrons in the outside ring. Okay. I always just tell students, think of it like when your stomach is full of food, you're stable, right? You're chemically satisfied. You're less likely to eat more and you're not hungry anymore, are you? Okay, that's where you're at that perfect spot. Okay. There is a set of 2 exceptions to that rule: hydrogen and helium. And that's because, remember, that first ring can only hold 2 electrons. Okay, so there is no second, third, fourth, fifth, sixth, eighth ring. You only have the first ring and you only need 2 to fill it up. Okay, and hydrogen has 1 electron, helium has 2 electrons. Okay, so they're the only 2 that are subject to that rule. Okay, the octet rule states that atoms with fewer or more than 8 electrons in their outer energy level are going to attempt to achieve chemical stability by either transferring, so in other words, gaining or losing electrons, or by sharing their outermost electrons. So they can give away electrons, they can take somebody else's, or they can just share them with a neighbor or with a friend. Okay. Chemical reactions enable atoms to do this, give up or require electrons, thereby completing their outer electron shells. The way that electrons behave enables atoms to in the body to exist in electrically charged forms called ions, or to join with each other into complex combinations of compounds and molecules. So here on the next page, I've got 8 examples, and we'll kind of just run through them real quick, and we can kind of try to figure out if that atom in its state is chemically stable, or if it's going to try to do something to make itself stable. Okay, so here is our first hydrogen. Atomic number is 1. It tells us it has 1 proton. 1 also tells us that it has 1 electron, correct? In this state, is hydrogen going to be satisfied? Is that outer ring the only ring that it has full?
No.
No. How many can go in that first ring?
2.
2. So 1 is not 2. Everybody agrees with me when I say that, right? So at this point, hydrogen is not satisfied. Okay. what it can do is gain one. It could share another one with somebody else. Or it could just get rid of its one altogether and not have any electrons whatsoever. Okay. A carbon, this is the one we were talking about earlier, has atomic number of 6. As I told you already, 6 protons, 6 electrons. So 2 go in the first ring. Then the remaining 1, 2, 3, 4 go in the second ring. Is carbon satisfied? Happy? Is it full? No. How many does it need to get in its outside ring? 8.
No, 8, no.
8. You always need 8 in the outside ring. 4 is not 8, is it?
No,
Okay, good. What about nitrogen? Nitrogen has atomic number 7, so 2 can go in the first. Then that leaves you with 1, 2, 3, 4, 5 in the outside ring. Is 5 8? No, obviously not. So how many more would nitrogen need to be satisfied?
1,
No. It needs 3 more. Okay. It needs 8 in the outside, not 8 total. 8 in the outside. It's got 5. So it needs 3 more to get to that 8 number. Okay. Oxygen has atomic number of 8. 2 can go in the first. 1, 2, 3, 4, 5, 6 can go in the outside ring. Is oxygen satisfied?
no,
No, because it needs how many more?
2,
2. Is everybody following along and understanding this? Okay, good. Now let's see some bigger atomic numbered atoms. Sodium has atomic number of 11, so it can get 2 in the first ring. 8 can go in the second ring. 2 plus 8 is 10, but it's got 11, so we have to make a third ring because that second ring is now full. Okay, is the valence, the outside ring of this atom, happy and satisfied? Is it
No.
full? No, it can fit 8. It has 1. What do you think is going to be easier for it to do? Get 7 more? Or how about it just gets rid of this one?
just get rid of that 1.
Let's get rid of that one. Okay. Well, look at chlorine. Chlorine is going to be the exact opposite of sodium. Chlorine has atomic number of 17. 2 can go in the first. 8 can go in the second. There's 10. We have 7 more. 1, 2, 3, 4, 5, 6, 7. 7 is not 8, is it? Pretty close though. 1 can fit right here. Guess where that 1 from here can go? Right there. Okay. Potassium. Potassium's a lot like sodium. Atomic number 19. 2 in the first. 8 in the second. 8 more in the third. 2 plus 8 plus 8 is 18. We need 1 more ring. There's the 19th. There's 1 in the outside, just like sodium. It's just easier to get rid of that 1, isn't it? Okay. Iodine is just like sodium. I'm not going to run through it all. Let's just go to the outside. There's 1, 2, 3, 4, 5, 6, 7 outer electrons. Is it happy? No.
No,
You can fit 1 more right there, just like chlorine could. Okay. Now these bottom 4 are all going to take place in the formation of an ionic bond, and they are all going to become ions. Let's talk about that now. This is going to be our first discussion on a chemical bond. Okay, ions are defined as atoms that carry a charge due to an unequal number of protons and electrons. In other words, the number of protons does not, there's a strike through that equal sign, equal the number of electrons. Okay, so going back to this previous page, in this state that we show them at, atomic number tells you the protons 11, 17, 19, 53. But that also tells you the number of electrons. Okay, so in the case of sodium, it has 11 positive charges and 11 negative charges. But we said that sodium's gonna just get rid of that guy right there, that outside electron. So is it gonna be neutral anymore? No, because it loses a negative charge. It's going to become positive, actually. Okay. That process where an electron is moved is called ionization. Okay. Transfer electrons from one atom to another to increase the stability of the valence electron layer. In other words, to satisfy, remember the octet rule. So here's sodium getting rid of that outside electron. So now it's got 11 protons, although they're not shown in this picture. 11 positive charges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 negative charges. Plus 11 minus 10. That's why you see the positive note symbol right here. Okay, it's got a +1 charge. Okay. Sodium is an example of a cation, an atom that has lost an electron and thus is now positively charged. Okay. Chlorine, we just described this on the previous page, needs one more electron right there. So here comes that electron that's donated by sodium. It gains one extra negative charge. So it now will have a net negative charge, and then we will call chlorine an anion. I don't really know why, but when you go from neutral to an anion, so when you go from chlorine, you actually will change it and call it chloride. Okay. I don't know why they add the "ide" at the end. I've never really cared enough to look, but you've probably heard of like fluoride before, like fluoride that's, you know, in toothpaste, and that's just fluorine. Now it's got that extra ion and it's got that extra electron, and now it's negatively charged. If you've ever heard of iodide, chloride, fairly common. Now, what do we know about our love life and that motto I said at the beginning of the lecture? Opposites attract. A positively charged ion and a negatively charged ion are oppositely charged, aren't they? And look what's going to happen if those two come into close proximity with one another. They're going to form what's called an ionic bond. An ionic bond is simply the strong electrostatic force binding positively negative charged ions together. In other words, if you wanted to just write this out, opposites attract. Okay. When something negatively charged and a positively charged ion come together. Okay. In general, they exist as solids, like what we saw at the bottom of that page, with a whole bunch of sodium and chloride ions bonded together in a cluster, which I said earlier, sodium chloride we commonly call stable salt. Okay. In the body, ionic bonds are found mainly in our teeth. Okay. We all know calcium is in our teeth, right? You hear that when you're kids. Drink your milk. Okay, get your calcium. Calcium is Ca2+. That means it's actually lost 2 electrons. 2+ means it's got 2 positive charges. Okay. Calcium likes to bond with phosphate, and it likes to bond with some other stuff. Okay. And that, as you guys have heard, gives great strength to your teeth. And then other ions in the body, you also see that ionic bonds give good important structural strength to them. Now, what happens to salt, for example, if you dump it in a glass of water? It dissolves. Okay. Ionic bonds are not strong to the point where they're going to resist water. And the reason that they dissolve is because those bonds break. We'll find out in our next lecture why that is. And that's what forms what we call electrolytes. I'm sure you've all heard, it's like a Gatorade commercial, and they talk about electrolytes. They're just talking about ions. Okay. Gatorade, for example, just has lots of salt in it. It's also got a lot of sugar and other stuff in there, a lot of water. Okay. But the reason that Gatorade is so helpful when people work out and exercise, because when you sweat, you don't just lose water, you're losing salt. If you have an old hat, I have several old hats, they have like the white rings on the inside of them from when I sweated and it's dried, and you can see that it's not just water that we're sweating out. Okay. Our body, as we talked about in our previous lecture, is super watery, inside the cells, outside the cells. So if you have ions in your body, more than likely they are dissolved in a solution inside the cell, outside the cell. So they're dissolved in our body fluids as electrolytes. Okay. This semester, we're going to deal a lot with hydrogen ions, sodium ions, potassium ions, talk a little bit about calcium ions. Bicarbonate, we talk about phosphates. We don't talk about all of them in great detail. But those are the common ions of the body there in that table. Not something you need to study or anything like that. So that's our first type of bonding. A strong formation, but not nearly as strong as the formation that exists with this type of bonding, covalent bonds. Covalent bonds are the strongest bonds that we have in our body. Covalent bonds are chemical bonds formed by the sharing of one or more electrons between valence electron layers of two atoms. I said one or more pairs of electrons. I want to make sure I emphasize pairs. How many is in a pair? Two. Okay. So we're not completely losing, we're not completely gaining electrons, we're sharing them. Okay. And we share them in pairs. Okay. A single pair would be two. Okay. And a single covalent bond is illustrated here with figure A between two hydrogen atoms. Remember, hydrogen has one electron. Well, it's not satisfied until it has two, right? Okay. If it gained another one, it'd be perfectly happy. But instead of gaining one, how about it just hooks up with another hydrogen? They share those two electrons. That way, this one's happy and this one's happy. Okay. They're both happy, absolutely. Okay. A double covalent bond is shown here in figure B, which is showing you the formation of O2. Oxygen gas shares 4 total electrons, the ones shown here in red, or 2 pairs. Okay. If we go through and count them up, there's 4 right here, 5, 6, 7, 8. This oxygen's happy. 1, 2, 3, 4, 5, 6, 7, 8. This one is happy. Okay. Letter C, this figure is showing you a triple covalent bond, which means that we're sharing 6 total or 3 pairs of electrons. If we went through and counted them up, 6, 7, 8. This nitrogen's happy. 6, 7, 8. This one's happy. So this is showing you nitrogen gas. Actually, these 3 are all gases that you might find in the atmosphere. Okay. Now, you can share covalent bonds in pretty amazing ways. What we see, and you're going to see this a lot in the next lecture, is that carbon and hydrogen like to covalently bond with other things. Not just with each other, but, for example, carbon and hydrogens hook up. And an example of that, where you've got one carbon single covalent bonded to 4 different hydrogens, forming what's called methane. Methane is what we call natural gas. Okay. We call things that are predominantly made up of hydrogen and carbons hydrocarbons. Okay. Guess what's in a carbohydrate? But you probably never thought about why we call them carbohydrates. Okay. It's got a lot of carbon and it's got a lot of hydrogen. So do fats, so does DNA, so do proteins. Okay. This is me getting ahead of myself, but I wanted to mention that. Now, sharing of electrons is a lot like sharing toys between two kids. And you're going to find that I like analogies. So I try to use as many of those as I can. I have two young boys, one's 5 and one's 3. Okay, and so there's always fighting going on about who's playing with which toy and whatnot. Okay, generally, big brother is going to win the fight because he's bigger and stronger. Okay, and if you had siblings growing up, you understand that relationship, whether you were the big sibling or the little sibling. I was the third of 4, so I had a big brother and sister and a little sister. So I was on both ends of the spectrum. Okay. In a non-polar covalent bond, the electrons are shared equally. Okay, which means the electrons spend equal time around each nucleus, and it's relating back to that opposites attract situation. Okay, or motto or theme, whatever. Okay. So in our illustration here, we have carbon and carbon bonded together. Okay. Well, if we say opposites attract, we could be just talking about protons and electrons. Okay, so protons have what charge again? Positive. Electrons are negative, right? Okay. Well, in the nucleus of this carbon atom are 6 protons. How many would be in this? 6. Okay. They have the exact same number of positive charges. That means they're they have the same strength. Okay. It's like 2 equally sized, 2 equally strong kids fighting over the same toy. There's a tug of war going on in which, nobody's going to win the battle. Okay. The electrons are going to be shared equally as a result. Okay. In a polar covalent bond, there is not sharing equally occurring. Okay. And what happens is a negative charge becomes present on the atom or the side where the electron spends the most time. Okay. Looking here, we have oxygen and hydrogen bonded together. Okay. Oxygen, I'm just telling you right now, because I know this has atomic number of 8. So it's got 8 protons. How many protons are in hydrogen? You guys remember? 1. That means there are 7 more positive charges here. There's only 1 here. There's 8 versus 1, 7 more over here. So where are the electrons attracted to? Where are they going to spend more time? Around the oxygen. Okay. This is the exact same thing that happens in my house with my oldest son. He's playing with the toy and I say share, and he's playing with it. He says, I am sharing. And little brother's just staring at him because he doesn't get to play with the toy. And he's there and he's part of the playing. Is my youngest son actually getting to play with the toy? No. Okay. So the electrons are here around hydrogen, but they're not fully around it. Okay. They're not as around it. Okay. And what that does is it creates a distinctive charge on this side versus this side. Okay. See these little symbols down here? Okay. The symbols down here, think of them just like slight or little negativity. So a slight negative charge, a slight positive charge, because there's the electrons on this side. The electrons bring a little bit of negativity to this side of the molecule. Therefore, since the electrons aren't quite as over here, this side becomes slightly positive. Does that make sense? Now, it's not perfect, and really, like I was already saying, the chemistry teacher would probably yell at me if I was saying this, but think of the terms nonpolar and polar, which we're going to talk a lot about in this class. And if it helps you, you might write this down. Nonpolar, think like no charge. Whereas polar, think charged. So nonpolar would be like neutral. Polar, think not neutral. It's got a charge, even if it's not fully charged. Okay. Now, when I say fully charged, something that's fully charged would be like these different ions. Okay. They are fully plus 1 charge, minus 1 charge, plus 2 charge, okay? In the case of these polar covalent bonds, it's not a full charge, it's just a slight charge. That's why this little symbol is there. Does that make sense? Okay. Now, non-polar and polar covalent bonds are the two forms of covalent bonds. And this polar covalent bond situation affects the third and final form of bond that we'll talk about, what we call hydrogen bonding. So polar covalent bonds that form between hydrogen atoms and other atoms give rise to a third type of chemical bond, what we call a hydrogen bond. A hydrogen bond forms when a hydrogen atom with a partial positive charge attracts the partial negative charge of neighboring electronegative atoms. Most often those are large oxygen and nitrogen atoms. Okay. It has everything to do with hydrogens, obviously, hence the name hydrogen bonding. But it also has everything to do with that motto theme, whatever you wanted to say it. And I introduced you on that first page, opposites attract. Okay. Hydrogen bonds result from the attraction of oppositely charged parts of molecules rather than from sharing of electrons like in covalent bonds or the gain or loss of electrons like in ionic bonds. Okay. Type this up. Hydrogen bonds are examples of what we call an an intermolecular bond. Intermolecular bonds. We learned this prefix the other day. Inter means what? Not inside, that's intra. Inter means between. So an intermolecular bond are bonds between already formed molecules. So intermolecular means between molecules, okay? They bond molecules together. They don't form molecules. Okay, so what do I mean? Well, we form a molecule this way through covalent bonds, sharing electrons. That makes a molecule. Or through ionic bonding, okay? Like with sodium and chloride coming together, forming sodium chloride. That's a molecule, okay? Water is made using polar covalent bonds, like what we show here at the bottom. Here's a covalent bond between oxygen and a hydrogen, and that same oxygen and another hydrogen, H2O. So here's one water molecule. Okay, here's a water molecule, here's a water molecule, here's another water molecule, here's another one, here's another one. These dashed lines that you see here, those are hydrogen bonds between these different already formed molecules. Does that make sense? So you've got water here, you got water here, you got water here, you got water here. They're attracted to one another. You're not making the water via a hydrogen bond. They're just attracted to one another, okay? Notice the dotted lines are between the big red blobs and the little gray blobs, okay? It's not red to red, it's gray to red, gray to red, gray to red, gray to red, okay? And that's because the little gray blobs are the slightly charged hydrogens, slightly positively charged hydrogens. The oxygen, the big red blob, is slightly negative. And what do we know about opposites? They attract, okay? Hydrogen bonds are weak in comparison to ionic and covalent bonds. So they don't bind atoms into molecules. Like I said, they don't form molecules. Instead, they help link molecules together. They're intermolecular, okay? Now, they're weak because this attraction, they're not connected to one another directly. They can break. But, okay, here's another example of an analogy, okay? Middle school and high school dances, and a boy is in love with a girl, or whatever. Okay, they're dancing super close to one another. The teacher or the principal comes by and says, "Okay, spread out a little bit." Okay, they separate. They get a little air between them. The principal or the teacher goes away. What happens? They go right back together. Okay, these bonds are breaking all the time, but then they're coming right back. Okay, this explains why boiling water takes a little while. Yeah, you put a pan of water on the stove, you turn the stove on. How long does it take for the pan to get hot? The pan, not so much. The water, yes. Okay. This explains why humidity is a thing. And we're going to talk about this stuff in our next lecture. Okay. So hydrogen bonds between neighboring water molecules give water very special properties that we'll discuss more in the next lecture. Okay, now going back to this slide, when we first introduced what a chemical bond is, says forces that hold together the atoms of a molecule or compound. So when we're forming a molecule like O2, or when we're making water, H2O, okay, chemical reactions are what enable atoms to give up or acquire electrons so that they can complete their outer electron shells. Anytime we're doing electron movement or sharing electrons, we're performing a chemical reaction. Okay, chemical reactions cannot create or destroy matter. They only can rearrange it. This is what we call the law of conservation of matter, one of the most important laws in all of the field of chemistry. Okay, what this means is you're not going to see hydrogens and oxygens coming out of nowhere. Okay, like what's shown in this figure. What you start with better be what you end with. In other words, we see 4 hydrogens here. We better have 4 hydrogens over here. We have 2 oxygens here. We better have 2 oxygens here. They might not be in the same manner that they were previously or before the reaction, but they better be in there somewhere. Okay. Cells are constantly rearranging molecules by breaking existing chemical bonds, like the bonds here between those hydrogens and this oxygen, and forming new ones. Okay, this is an illustration showing you a chemical reaction. They always use an arrow to describe the direction in which a reaction is occurring. Okay, the direction this way tells you that this is what we start with, this is what we ended with. The starting materials in a chemical reaction are called the reactants. The ending materials are what we call the products. We started with 4 hydrogens, we ended with 4 hydrogens. We started with 2 oxygens, we end with 2 oxygens. Make sense? Okay, that's the law of conservation of matter. Here on the next page, we're going to talk about the law of conservation of energy. Each time a chemical reaction occurs, energy is going to change form. Now, what is energy? It's the capacity to do work. And there are two principal forms of energy that exist: potential and kinetic. Potential is energy stored by matter due to its position. Okay. A lot of times students describe and people describe potential energy as energy at rest. If it helps you write that down, go ahead and do that. Energy due to position or energy at rest. And that's used because kinetic energy, which is the opposite of potential, is associated with matter and motion. So think of like a ball on top of a hill, resting due to the effect of gravity. It's got a lot of potential energy. And if you just give it a nudge, what's going to happen? It's going to roll down the hill, right? That potential energy is going to get transferred. It's going to get changed from potential into kinetic. Okay. Now, the most important form of potential energy in this class that we'll talk about is chemical energy. Is a form of potential energy stored in the bonds of compounds and molecules. It's all about the position of those electrons, because electrons give energy to molecules and compounds. Okay. Thinking about energy for us, where do we get our energy? From food. Absolutely we do. Guess what food has a whole bunch of? Potential energy in the form of chemical energy. Carbohydrates, proteins, and fats, specifically. Now, if somebody would have said when I asked where do we get our energy, and you said the sun, I would have accepted that answer. Because that's where all energy originates for us. Okay. The sun provides energy that comes down to Earth in the form of light and heat. Light and heat are both examples of kinetic energy. Now, we can't just sit outside and get energy from the sun, but who can? Plants and algae, right? They make their own food. And that process is called what? Photosynthesis. Now I'm getting in the weeds here. I guess that was a pun on accident, but they make the energy and we can either eat them like in a salad, or we can eat a cow through some steak who ate them. So it's all about just transferring energy. Okay. Your car needs energy. What's your car use for energy? Gasoline. Guess what gasoline is the equivalent of? Food. It's just got a lot of potential energy in it. And then when your car drives, that's motion, right? When we move, that's motion, right? We convert potential energy into kinetic energy all the time. Now, the law of conservation of energy states that energy can neither be created or destroyed. So it's just like matter. It's only converted from one form to another. Conversions of energy from one form to another generally releases heat, some of which is used to maintain normal body temperature. Okay. And when we do things like exercise and we're doing a lot of converting from potential to kinetic, what do we experience? A drastic rise in body temperature, right? We get hot when we exercise, correct? And we start sweating as a result, right? That's an example we've all experienced. And we are warm-blooded. Everybody's heard that phrase before, right? And that's because we take the energy that we give off in the form of heat and we try to keep it and keep our body temperature elevated around 37 degrees Celsius. Whereas cold-blooded animals, how do they get their body heat? They have to sit out like on a log or on a rock, like you see frogs and alligators and turtles and stuff like that doing. That's okay for them, but do you see frogs and turtles outside right now? So not a lot of heat to absorb, is there? And so humans and other mammals have the ability to stay active year-round despite environmental changes. Chemical bonds represent stored chemical energy, and chemical reactions occur when new bonds are formed or old bonds are broken between atoms. Basically what I've already been talking about. The overall reaction may either be a release of energy or absorption of energy. The two terms exergonic, endergonic will be used at various points this semester. Exergonic reactions release more energy than they absorb. So energy is given off. Think of it's like I tell students exit. It's exiting, it's being released, it's leaving. Okay. Endergonic are going to be reactions that absorb more energy than they release. So the energy is pulled in, it's absorbed. Okay. So those are the opposite of one another, which relates to metabolism. Something that I introduced in our last lecture, and I told you guys we'd talk more about it. Well, here we are ready to talk more about it. The term metabolism is one of those 6 basic life processes that we talked about in our last lecture. We learned that it is used to describe all chemical reactions occurring inside of our body cells. We also learned that there's 2 forms or 2 phases, catabolism and anabolism, or catabolic anabolic reactions. Catabolism are those chemical reactions that break down complex organic molecules into simpler ones, which are exergonic, meaning that they release the energy stored in the organic molecules. We just learned exergonic release more energy than what is absorbed. Okay. Catabolism is where we go from something bigger, like a dimer. A dimer is just where 2 things are bonded together, breaking them down into 2 smaller things, or in many cases, it's a lot more than just 2, because it's not always just 2 to 1 and 1. Maybe it'll be, 10 to 1, 1 to 1 to 1. Okay, all the way down to 10 different ones. Okay. In other words, we can say we break covalent bonds and produce smaller molecules. And what's not shown, but is always going to be involved, is what's happening with energy. In this case, it's exergonic. So energy is released and it's useful. This is what we do to energy in the form of ATP that's the energy that powers everything we do. Okay. In this process, a process called hydrolysis occurs, which is where not only are we breaking down complex compounds, but we're also releasing energy in the form of ATP. Hydro is a prefix that means water. Here you can see H2O. Okay. The components in water, the hydrogen and the OH, are what help to split the monomers apart from one another. Okay. Anabolism is the opposite of catabolism. These are chemical reactions that combine simple molecules. So it's just the opposite of what we saw here. It's monomer 1, monomer 2, forming the dimer. Okay. So it's combining simple molecules and monomers to form the body's complex structural and functional components. Instead of exergonic, these are endergonic, since they consume more energy than they produce, which means they actually require energy in the form of ATP, which we'll talk more about. The ATP that is going to power these reactions generally is formed back here in catabolic reactions. Okay. Instead of hydrolysis, where water is used to break things apart, we call this dehydration synthesis. If you are dehydrated, it means you are lacking what? Water. So you're removing water to synthesize, to build up, and that's what happens during anabolic reactions. We just have like 2 or 3 more slides, right? Does anybody have anything specific they gotta, can we just finish it? It'll take me just a few more minutes, as long as that's okay with everybody. Okay, let's just buzz through. Like I said, it'll take 5 minutes or so. All right, a key feature of our body's metabolism is the coupling of exergonic and endergonic reactions. And you can see at the bottom of the illustration, it's a cycle of events. They go together. The energy released from an exergonic reaction, so going from a complex molecule to simpler ones, okay, we form ATP, okay? Catabolic reactions break things down. Heat is released. Everything involved with chemical reaction releases heat, produces ATP. This is what we're going to do and talk about when we discuss glycolysis, electron transport chain, all that wonderful stuff. That ATP energy then can provide us the ability to build up from simple to complex, go from small to big. Okay? And then the same thing, anabolic reactions, just like catabolic, release heat. Thankfully, we don't just release that heat to the environment. It gives us our body temperature. Okay. We're going to see this exact same figure again later in the semester. We're going to talk about this exact same stuff again way later in the semester, though, when we get to that glycolysis stuff. So I just wanted to introduce it a little bit here. All right, the last thing I want to talk about are the 4 classes of chemical reactions. The first 2 listed there, we've already really covered. And the next 2, based on their name, hopefully are pretty easy to figure out what happens. Once again, a chemical reaction involves the interaction between atoms and molecules, in turn involves the formation or breaking of chemical bonds. The first type of reaction is called a synthesis reaction, where you're going from something smaller, like a single atom, bonding it to another atom or an ion to another ion. It's small, forming big, okay? Pretty straightforward. Example, A plus B yields AB, where A and B by themselves are small, AB is big, okay? Opposite of that is decomposition. It's just where the arrow is going in the opposite direction. AB broken down into A plus B. So when large molecule is broken down into smaller ones. Exchange occurs when 2 different reactants exchange components and as a result form 2 new products. Remember, reactants are the starting materials, products are the ending materials, okay? During exchange, both decomposition, so something's broken down and something is synthesized, it's built up. So like to go from AB plus CD to AD BC, the bond between A and B must break. The bond between C and D must break. And then A must bond to D, B must bond to C. So we're breaking down in building in that process. Okay, this is what happens, for example, with hydrochloric acid and sodium bicarbonate to form carbonic acid and sodium chloride. And then a reversible reaction is where we can go from one direction, forming products, and then we can reverse the reaction, hence the name, and form it in the opposite direction. So both sides are visible. That's why we've got an arrow going in both directions. Okay. Some reactions are reversible under certain conditions. You know, for example, something might go from AB to A plus B, like if it's subject to heat. Whereas if like you add water, it might go in the opposite direction. Okay. We're going to see this, what is illustrated down here on the bottom right quite a bit this semester, talking about ATP. ATP is adenosine triphosphate. This is our energy. We call it triphosphate because there's these 3 blocks, 3 phosphates. ADP is adenosine diphosphate, where there's only 2. Di means 2, tri means 3. Okay, the 3rd phosphate, PI, is right there. When we break down ATP, this is what we form. And then when we make ATP, when we make energy, we bond them together, and that's what happens when we go in that direction. Stuff we'll talk about quite a bit later on. For now, not so much. All right, any questions? All right, like I said, 5 extra minutes, so I appreciate you guys for hanging just a little bit extra. That's all I have for you guys, so have a great rest of your weekend.